Hi, everyone. Thank you for attending to our meeting. We are the Solar Savior Broncos team representing Santa Clara University, and we are going to present you the Ohio State University district case proposal. Next. Okay, here's our team, and today's speaking will be Ahmed, Saleh, Chris, and Joanna speaking. Next. Okay, our proposal has three major developments according to the Ohio State University requirements. We did 3 renewable energy applications, 2 PV application systems, one located on the east part of the campus for the medical campus of the Ohio State, and the other is located at the west campus, which is an agrivoltaic system design. We also were tasked to provide an energy storage solution in order to provide some resiliency to the campus. And in order to analyze the feasibility of our design, we also perform a financial analysis and a development plan. Next. Okay, for the Ohio State Medical Campus Center PV design, we consider several characteristics in order to perform our design, our conceptual design. The first thing we did, as you can see in the picture, we divided the area into 5 subsystems so that we were able to analyze on detail each particular area. For all of those, we analyzed several technical parameters such as the tilt and the orientation and the row spacing to try to get the most generation energy available for those rooftops. And also we consider the design having pathways in order to provide maintenance capabilities as well. Next. Okay, considering the previous considerations made, here is one snapshot of one of our designs, which is the area number 1. In this area, we located the critical loads of the Ohio State campus, which are the Wexner Center and the James Cancer Institute as well. As you can see, well, we use the Aurora software for the deployment of all of our systems. And as you can see, we place the panels on the areas with the best irradiance, which are the orange ones, the brightest orange ones. And we avoid the location of panels on those areas like the purple ones because they weren't good enough in terms of irradiance. We did this same approach for all of the 5 areas, and in total, we were able to produce a system with 5.2 megawatts of installed capacity, able to generate 4.4 gigawatts hour of energy per year. Next, please. Okay, for the agrivoltaic system design, we took a different approach, and considering that we were provided with 21 acres of land to design, we decided to analyze 3 characteristics that give us like the chance of have the most energy for an area, a particular area. So the first thing we did was to pick the flattest location, such that the design was like, the irradiance was the most uniform possible for our design. We also picked this location in order to facilitate the installation of the PV systems and also the maintenance of activities. We also consider for this design the irradiance. We picked a place with the most solar resource available. And we also consider or try to avoid as much as we could the need of relocating or tree trimming. With that regard, our system proposed is shown on the picture on the right. And in there, we were able to allocate 51 panels producing around 1.2 megawatts of energy capacity and power capacity with 1.4 gigawatts hour of energy capacity. We decided that those panels will be mounting on a canopy structure such that agricultural activities will be able to perform at the same time. Next, please. Okay, finally, for the energy storage application, we first decided or we needed to know the needs or the requirements for the critical loads. With that regard, we went ahead and analyzed the information provided in the data sets. We decided that the worst case scenario of our load consumption would be our target to design our energy storage application. So for that, we found that a system with 2.5 megawatts of peak power will be able to supply such amount of energy or power capacity. For the energy capacity, we went into the REOP tool and analyzed the financial side of the energy storage system. And we found that we were able to supply 4 hours of energy for that capacity during 4 hours with 91% of certainty. That means that we were able to design a system providing 2.5 megawatts peak power plus 10 megawatts hour of capacity for supplying 40% of the critical load. With this consideration, our proposal includes 5 battery containers, which will allocate several battery banks with lithium iron phosphate cells. And we decided to allocate this battery station on the backside of the Wexner Center and James Cancer, as you can see on the red square on the top. And with that, I will leave you with Saleh, who is going to explain you the distribution system.
The distribution system in general is radial, but for urban area, it can be meshed. Since Ohio State University has a combined radial and mesh distribution system, we considered 4.16 kilovolt voltage level for the distribution system. By the proposed PV system in Area 1, there is a 5.8 gigawatt hour of energy production per year. Besides, we have a 10 megawatt hour battery system that provides 40% of the peak critical load demand. Adding a big scale PV generation, a battery system can cause instabilities in frequency and voltage, especially in frequency. This can be addressed by some certain mitigation strategies. The sum of PV and battery power generation in each node is limited by hosting capacity by considering the average of 4.2 sun hour for fixed steel PV system with 83% DC to AC power conversion efficiency. For the Ohio State University, there is a 544 kVA PV power injection to 2 critical nodes. The battery system will kick in only in case of a fault or an outage. Also, the critical loads, PV and battery system will form an islanding microgrid once there is a fault or an outage. Once the fault is cleared or power is back to the lines, the islanding microgrid will reconnect to the main grid by means of static switches and synchro phase. Battery system will only be connected once there is a fault and there won't be any sort of power injection to the main grid. The high penetration of renewable energy system can lower the inertia of the system, which can cause instabilities in voltage and frequency. We can apply some mitigation strategies in inverters control systems, such as droop control or virtual inertia emulation, or adding something like synchronous condenser. We can increase the inertia and we can mitigate some of these instabilities. With that, I hand it over to Ahmed.
Okay, so in terms of our financial strategy, we've decided to prioritize resiliency over customer savings and economical benefits, and also achieving the maximum solar energy generation possible. And that's due to the critical load that was being supplied, including medical campus and hospitals where patients are being treated, and constant power supply is imperative. So despite the utility rate that OSU currently pays just being over 4 cents per kilowatt hour, shown in the figures on the right, in the blue line specifically, the power purchase agreement or PPA pricing was set to be at 8.5 cents per kilowatt hour for the PV only system with an internal rate of return of 10% and a total cost of $10 million. While with the solar plus storage, our proposed project presents a PPA of 12.7 cents per kilowatt hour with an IRR of 9.5% and a cost of $16 million. Both proposals have a payback period of around 10.5 years. In terms of the NPV or net present value, we met the requirements of having no net profit or loss for the PV only system. But for the solar plus storage system, the batteries were expected to cost around $6 million. So there's a net loss of around $200,000 after considering the avoided outage costs. These costs were calculated based on the average interruption costs for a commercial building in Ohio, the number of patients that are being treated a certain time within the medical centers on average, along with the utility company's average interruption indexes provided by them. So in terms of the development plan, it highlights the important steps taken to construct the system within a proposed timeline. And that entails a clear plan for land use, where it's divided into 6 sub-areas, as Joanna demonstrated earlier. And for the agrivoltaic system, we found that the soil consisted of silt loam, which presented suboptimal conditions for farming, as well as for PV installations. In terms of zoning compliances, OSU campus is located in Franklin County, zoning area Z88, under the category of research park and commercial property class. University also must follow the Ohio Building Code and Columbus City Codes, Title 41 for building codes and Chapter 4113 for permits and fees. Lastly, we found that the project aligns with OSU's master plan and their goals for clean energy use and sustainability, where they are aiming for 10 megawatts of solar energy generation by the year of 2030 in the campus. Following slide shows the proposed timeline for the project development and construction. The total period is 12 months, with the most important part being the construction taking place during the latter half of the year. With regards to risk analysis, we've tried to look for potential issues that might arise during the development and construction phases of the project. So some precautions were taken with regards to building permits and equipment delivery to avoid any delays. And we added an extra allocated period for obtaining them within the timeline. And similarly, the construction cost has been set at a price to avoid the likelihood of any unplanned increases. And of course, we based on the likelihood and impact of each risk and how to mitigate them. And with this, I leave you with Chris to talk about community engagement and to wrap up.
Hello. So how will the community actually engage with the solar system? For one, there can be solar installations on campus that could utilize the power that is being provided by these solar systems. And also further research can be built on top of what's already being provided by this strong foundation of storage and PVs. What's really useful and really important is the statistics that this university will gather by having these numbers on what their energy generation is for clean energy and their carbon offset through their future, through using this installation. Next slide, please. So what is everything that's in this design? Well, what is everything that's here? We have a 6.4 megawatt solar facility with 2.5 megawatts of battery storage capacity. This is including 1.2 megawatts of power from an agrivoltaic system in the pasture land. And this all combines into having 5.8 gigawatt hours of energy per year with 10 megawatt hours of battery storage. This is going to significantly reduce the Wexner Center's annual energy needs, and will also provide the resiliency that's much needed by the university, so that they could take an outage that's 4 hours long with a 95% certainty, and then a 6-hour outage with 90% certainty. This all comes at a PPA price of around 13 cents per kilowatt hour, and will significantly reduce the carbon emissions of the university by several tons. Next slide, please. Why does this matter, though? Our design fulfills the requirements and goals met by NREL and making something happen. And this is also being done in a financially sound and credible way that will have a low NPV value. But most importantly, this is fulfilling Ohio State University's mission to become a sustainable university and to lead in the clean energy space and achieve its sustainable mission. Thank you so much for your time. We really appreciate all that you've done for us. Have a great day.